My name is Juan Grau and my project partner is Marisa Kwiatkowski, and our project is called Reducing Influenza Propagation Through Air Travel Pathways. In our project, we sought to inhibit the spread of an infectious disease, specifically in this case influenza, through a network by removing select edges from the graph. Our work is inspired by prior papers on network interdiction. Specifically, Juan's papers focused on reducing the spread of infectious diseases through a network. One of the papers that we were very interested in was removed edges based on some of their more statistical properties within the graph, such as their betweenness centrality measure and their Jacquard index. On the other hand, another paper that we saw that was particularly interesting sought to minimize removed edges that minimize the total number of susceptible nodes within the graph based on a given set of infected nodes. And so we wanted to compare these two methods for removing edges by using a more robust flu simulation than either of the two papers used initially. So there are three methods that we implemented for removing edges in the graph. The first method we implemented removed edges with a low Jacquard index. We remove edges with a low Jacquard index because a low Jacquard index indicates a smaller number of common neighbors between the two neighbors, which in turn means that we protect more nodes from the disease in case one of those two nodes becomes infected. Another method we use to remove edges is based on the betweenness centrality values. Edges with a high betweenness centrality are more likely to transmit diseases through a network because there are a higher number of shortest paths that traverse that edge. And lastly, we implemented the minute risk algorithm laid out in the paper we mentioned. And in this algorithm, we basically iterate over all the edges and at each iteration, we remove that edge and estimate the final reduction in the number of susceptible nodes by random sampling. It's a very expensive algorithm because you're repeatedly iterating over all of the edges in the graph and removing them, and then doing random sampling. So the data sets we used two real-world networks of flight data. We really thought these would best solve our problem statement, which was to reduce the spread of influenza through a flight network. So we found that the US airport data set from 2002 and the Air 500 data set, which was a subset of a data set used in the paper that removed edges based on Jacquard index and betweenness centrality. We also decided to use a randomly generated Erdos-Renyi graph with 50 nodes and 150 edges. And this was because the minute risk algorithm we implemented was too slow to complete the algorithm with the two real-world networks, which each have 500 nodes. So we had to create a smaller network just to evaluate the minute risk algorithm. We decided for our model to use the susceptible, infected, recovered model for our simulation. Other papers have argued that the susceptible, infected, susceptible model is more applicable for the spread of the flu because over the course of the flu season, the virus can mutate and people can actually be infected multiple times. But we decided to only run our simulation for 30 days, which does not give the virus enough time to mutate and infect people multiple times. We found that the reproduction number is 1.7, which is basically the average number of people a person will infect once they are infected with the flu. In our simulation, we assume people are only contagious for 1 day. This is because when you're infected with the flu, you start becoming infectious or contagious a day before you start exhibiting symptoms. And we assume that once you start exhibiting symptoms, your probability of infecting more people goes down drastically because you're most likely interacting with fewer people and staying inside and mostly just caring for yourself because you have the flu. So this was a sort of a simplifying assumption we made that actually makes sense in real life. And we also use a simplifying assumption that each of our nodes starts with 100,000 people. And we also randomly select cities to start with the flu, and when they start with the flu, they start with a predetermined number of people who are infected with the flu. Our simulation, the flu spreads according to a formula used by Epstein in their paper, Controlling Pandemic Flu, the Value of International Air Restrictions. The formula allows us to calculate the number of newly infected nodes in a city. This calculation is done by summing the number of infected people in the city and multiplying that by the number of susceptible people divided by the total number of people in the city, and then scaling that entire value by the reproductive number. In our simulation, so each iteration of our simulation, we use this formula to calculate the number of infected people in the city, and then at the end of the day, each person travels to a neighboring city with probability 0.01. And so if some of the infected people travel, then the next day they will infect other people in the city that they traveled to. And we run the simulation for 30 days. So these are some of the results that we obtained. On the left, we have a table of sort of the number of infected people using the given methods on the 3 different graphs we used. So as a benchmark, we ran our simulation on our data sets without removing any edges to see how many people were infected. And then we tried removing edges using the methods we mentioned, and reran the simulation and calculated the number of infected people. As you can see from the table, the Jacquard, by removing edges by their Jacquard index and betweenness centrality value, did indeed reduce the number of infected people, but in the random graph, the min at risk algorithm proved to be the most promising, and unfortunately it took too long to run on the AIR 500 dataset in the US AIR dataset. And on the right, we have on top is a visualization of the original graph without having any edges removed, and running the simulation where each red node represents a certain number of infected individuals in that city. And below it, we have the same simulation run after removing edges based on betweenness centrality. And as you can see, there are far more nodes with very few or much fewer infected individuals, which is sort of like a visual affirmation that removing edges based on betweenness centrality does indeed reduce the number of infected individuals. For future work, one of the biggest improvements we can make is improving the runtime of the min-at-risk algorithm. When running on the random graph, it seemed like the min-at-risk algorithm far outperformed the other 2 methods. We think this is because it actually takes into account which nodes are infected, whereas the other 2 methods we use just use aspects of the network without any consideration of which nodes begin infected. But we can't know if this algorithm would outperform the other two methods on real graphs unless we can improve the runtime. Our susceptible infected recovered model for our simulation is definitely far from perfect. The city populations are oversimplified, and we only have 100,000 people in every city, and it would be really interesting future work to see how the methods compare when cities have varying populations, which is more realistic. And another simple future work would just be to run these simulations multiple times and measure the variance of the results. There's a lot of randomness involved in simulating the spread of the flu, and it would be good to measure how much the number of infected people changes from run to run. Thank you so much for your time and for helping us through this class. Please reach out to either me or Marisa if you have any questions. Thank you.